Hey everyone, welcome to the lecture for 2.4 on arc length and surface area. So in order to get to the point where we can compute surface area for a curve revolved around a line, typically an axis, we need to determine how to get arc length. And so arc length is really just the idea of adding up these small little straight line segments. So we can see it here in this figure 2.37. You're just adding up these small little straight point segments. So how do we connect that idea to theorem 2.4, where we see the formula for arc length? So 1 plus f prime of x squared, quantity square rooted, integrate from a to b with respect to x. So let's kind of look at that a little bit further. So if I have, I'm going to zoom kind of way in on a hypothetical curve f of x. So let's say this is a really up close look at f of x. So if this is some value x, and let's say this is another short time later, this is x plus delta x, right? So delta x then is meant to be really small. Some really small distance between these two x values. Then what I would have is the function at these two heights given as f of x, and I wish I had scooched this thing over before. And the second height is going to be f of x plus delta x. So even though I can't truly say what this length is between these 2 points, I can estimate it by drawing the secant line here. And using the Pythagorean theorem, I can actually tell you how long this segment is. So the way I do that is I just construct a right triangle. I suppose x plus delta x is really here. We know that this distance for the base is delta x. And in order to get the distance for the height of the other leg, it's just going to be the difference of f of x plus delta x minus f of x. So then I just want to use the Pythagorean theorem. So this is going to be this is going to be the square root of delta x squared plus f of x plus delta x minus f of x squared, right? And so that kind of looks like a lot. You're like, oh my goodness. But we're going to make it look even worse, and then it'll look really good before you know it. So bear with me a little bit. So the length of that segment, just rewriting it, is going to be delta x squared plus, I'm not doing anything yet, just rewriting, just rewriting what we have below. All right, so the next thing I'm going to do is I'm going to factor out a delta x squared. And you might be thinking like, well, there's no delta x squared in the expression involving f, which is true. So if I divide by it, then I have to put it in the numerator. Check this out. So as promised, it's looking worse before it's looking better. But we did successfully pull out a delta x quantity squared. And I'm going to now slip that out the back of the radical. So just to be clear, I have, this is the structure. I have a plus b times c squared. And I'm saying that's equal to a plus b times c on the outside. So this is what I'm going to employ here, taking the square out of the square root via multiplication and making sure to cancel out that square symbol. So now I have the square root of 1 plus, and the other cool thing I'm going to do, if you think playing with fractions is cool, is I'm going to write a fraction, like, so here what we have, the f of x plus delta x minus f of x, that guy squared over delta x squared. So that's kind of this a squared over b squared form. I'm going to write it as a over b quantity squared. So like that. And I'm hoping that this is starting to look a little bit familiar. You may be thinking, I've seen that before, but there was like an H somewhere. And you would be exactly right, because the thing I just wrote down in the brackets is the difference quotient. Let us not forget that we had a delta x out the back. Perfect. So now as delta x gets really small, and when I say really small, I mean like calculus version of really small, infinitesimally small, like a limiting process. What we're going to have is that this becomes the square root of 1 plus f prime of x squared, right? Because that was the difference quotient. And as the difference quotient, as your secant, your points that form your secant get closer and closer together, you become the tangent line. The tangent line is the derivative of a function at a point. So this is f prime of x. And don't forget, we squared the whole thing. So we've got 1 plus f prime squared. And then we're going to think of our delta x as becoming d of x. And I know I'm using a little bit of imprecise language, but that's kind of like the flow I want you to think of. Just look at it from a Pythagorean theorem standpoint of just a triangle, an anneal triangle. Now let delta x get super small. Now consider that you have a difference quotient where delta x is getting really small. Okay, call that the derivative. Okay, now add them all up. And then the fancy way to add them all up, that's just integration. So that's where that comes from here. So let's actually use the arc length formula and see it in action. So these are pretty straightforward. Because the formula is a to b, the square root of 1 plus f prime of x squared dx, it's almost like a plug and chug. Like, okay, what are a and b? Boom, boom, a, b. What's f prime? Well, if f of x is 2x to the 3 halves, then f prime is going to be 3 root x. And now we just need to put it into our formula. So we're going to have the integral from 0 to 1, the square root of 1 plus f prime squared. So we can even go ahead and kind of do that out right here on the side. This is just going to be 9x. And then now this is just a u substitution. So we're going to let u be 1 plus 9x, then du is 9 dx. So we get 1/9 du equals dx. We also have our limits of integration. So u of 0, so if I plug in 0 for x, I would get 1. And if I plug in 1 for x, I would get 10. So this is going to become the integral from 1 to 10 of 1/9 root u du. And so we can just finish this off with the integration. So 1/9 times 2/3 times u to the 3/2. Evaluated it from 1 to 10. So let's call this 2 over 27. So we have 10 to the 3/2 minus 1 to the 3/2. So we get 2 over 27 times 10 root 10 minus 1. And this is approximately 2.268. So that's it. It's really kind of just a plug and chug, follow the rules situation. You can do the exact same thing if you have your function as a function of y. There's really no change. So here we have g of y equals 3y cubed. So we get that g prime of y is 9y squared. G prime of y squared equals 81 y to the 4th. And then we can just set up our integral. Not going to integrate because, well, you'll see in a second. So it tells me my interval is 1 to 2. I plug it into the Pythagorean theorem. And this is kind of like not easily integrable. It would end up with kind of like a inverse hyperbolic trig function. But anyway, so just an idea to kind of practice setting it up. No, I'm not going to give you a integral where it's a inverse hyperbolic trig function on the exam. So, okay, so now that we kind of have the idea of how to compute arc length, that's really just a stepping stone for us to get to surfaces of revolution. So previously we did solids of revolution. So those were three-dimensional objects that had 3 dimensions, like I said, that have volume, that are kind of like in the cubic space. This is going to be more of like a sheet of paper that's infinitely thin. So let's kind of think about what all this means. So I have 2 pi f of x and then times our old friend square root of 1 plus f prime squared. So if I have, let's see, just as an example, if I have some function, this can be f of x, and on an interval from a to b, I want to rotate this around the x-axis. Then what I'm looking at, maybe think of it like a vase or a pitcher, where we're not really considering the width of the medium. It's like infinitely thin. So it's just surface area, not volume at all. And the way that you can try to imagine where this formula comes from is, as we did before, you kind of just take a little strip out. So kind of just take a little strip out. And this isn't a cylinder, it's just kind of like a strip of tape or a strip of paper, or like imagine wrapping some toilet paper around your face. You know what I mean? Then you can kind of like take that and you would just have this little like long rectangular strip of paper. So that's what we're doing here. So we have our little strip of paper. And we want to know the area of it. So what we can do is as before, you can kind of take scissors to it. And you can just like cut along anywhere along the edge. And if you were to unwrap it, you would end up with kind of just a long, narrow piece of paper, whatever you want to call it. So this little width here, well, actually, let's think about this. This little piece here comes from this little piece here, right on the curve. I'm going to scroll up. That little piece on the curve, that was estimated by this secant line here. That little secant line was given by this one here, right? So stay with me. So this is, you should really think about this as coming from 1 plus f prime of x squared dx. Even though we haven't really applied the limiting process yet, I'm still going to write it as dx just so we have a better matchup in the formula. So we know that it was originally delta x, and then we let delta x get really small. Okay, we have another dimension, right? So this is surface area. So we have the width, we need the height. This is actually the same thing as the circumference, right? So this is the circumference. And we know that circumference is pi times twice the radius. And the radius comes from here. So the radius is just the height of the function itself. So it's 2 pi times f of x. So now what we want to do is we kind of want to add up all these together. So imagine like taking this in like, imagine taking a solid and like wrapping it in little tiny sheets of tissue, kind of like mummy style. Like, I don't have any money, but I need a Halloween costume mummy style. So you're taking all of those kind of strips of toilet paper and kind of counting up the surface area of them individually. So that's what you're doing. So maybe you have another strip here. Then you have another strip here and here. So now you just have all these super teeny tiny little strips of paper, and you're adding up all of their surface areas. So again, because we're in Cal 2, this idea of adding things that are super, super, super small solidifies into the idea of integration. So what we end up with is you just have the integral from a to b of all these little areas, which was 2 pi f of x, right? So this was your circumference. And then 1 plus f prime of x squared dx. And this was, we were thinking about this as the width. And that's it. And so that's exactly what we're going to see when we reference this theorem. So that's it right here. You could have done the same thing in terms of y, same structure, different variable. Okay, so let's do an example. So f of x equals the square root of x, blah, 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 blah. Okay, let's graph it. We're going around the x-axis. I know I'm going from 1 to 2 and from 1 to 4. So I'm here, here. So basically what this looks like is just, I don't know, like a unique little lampshade, I guess, how maybe I might describe it. Again, not a solid, just a surface area, an infinitely thin lampshade. So this is f of x equals the square root of x. Okay, so what do we need to do? We just need to add up all those strips. We don't need to parse it out each time. We can kind of just follow the formula. So we're going to have that f prime is equal to 1 over 2 root x. Then f prime squared is 1 over 4x. And so if I kind of put this into what we discovered to be the structure for computing the surface area, I would get 1 to 4, 2 pi times the radius. The radius was just a function, which was root x, times the width, which was the square root of 1 plus 1 over 4x dx. And so now I'm going to push in this x. So just the principle I'm using here is that if I have the square root of a times the square root of b plus c, I get the square root of ab plus ac. Conversely, if ever I had a times b plus c, I guess not conversely, alternatively, I'd have a squared b plus a squared c. So I'm going to go ahead and use that, the first line that I said. So I have 2 pi from, so inside my radical, I'm going to get x plus 1/4. dx. So you could do a u sub here if you wanted to. Probably we should. If you feel comfortable not doing a u sub and kind of just making a mental note in your head, that's fine too. So if I do a u sub, I'm going to let u equal x plus 1/4. Then du equals dx. U of 1 is 1 plus 1/4, so that's going to be 5/4. And then u of 4 is 4 plus 1/4, so I'm going to get 17 over 4. And so my new integral becomes 5/4, 17/4 as my limits of integration. Then I get 2 pi root u du. So this is going to be 2 pi times 2/3 u to the 3/2 from 5/4 to 17/4. This is probably the hardest part of the problem right here, actually. So we're going to get 4 pi over 3. And then just really quickly, a over b to the n. I'm sure everyone knows this already, but a to the n over b to the n. So I'm going to get 17 to the 3/2 over 4 to the 3/2 minus 5 to the 3/2 over 4 to the 3/2. And so now we have a common denominator instead of something hideous. 4 to the 3/2 equals 4 root 4. So that's 8. So I get 4 pi over 3 times 1/8. They both have a 1/8, so I'm going to go ahead and factor that out now. 17 to the 3/2 minus 5 to the 3/2. So I get pi 6. And 17 to the 3/2, that's just 17 root 17 minus 5 root 5. Do I have an approximation for that? No, I don't, but have fun with your calculator. All right, so the next example is, oh, our last example, nice. So this is going to be in terms of y. So we have the cube root of 3x, but we're going around the y-axis. So that means that I'm going to need this to be in terms of y. So the first thing I'm going to do is convert f of x into g of y. So what I'm really saying here is I don't want to have my function in terms of variable x. I'd like it to be a function in terms of variable y. So if I have y equals the cube root of 3x, then I can cube both sides. So I'll get y cubed equals 3x, divide by 3. Y cubed over 3 equals x. So g of y is just y cubed over 3. Perfect. So now I'm ready to begin, because what's really going to happen, I think it looks like this. Like the cubic function looks like that. So scale it as you will. Y is going to go from 0 to 2. So you look like this. So your little strips are kind of coming around this way. So in order to compute this surface area, we need to know what g prime of y is. So we're just going to get 3 comes out, cancels, so we get y squared. So g prime of y quantity squared equals y to the 4th. And now we can kind of just put it all together. So I'm going to get, so we're told that y goes up to 2. So we're going from 0 to 2 pi times g of y, which was y cubed over 3. Right, so that first bit we just did, this is our circumference here. This is going to be our width here. So I'm going to get 1 plus y to the 4th dy. And now I need a u sub so I can integrate. So we're going to let u be 1 plus y to the 4th. So that du becomes 4y cubed dy. So this is good. I'm just going to go ahead and solve it for y cubed dy. So I'm going to get 1/4 du equals y cubed dy. Then I also have that when x is 0, u is 1. And when x is 2, so 2 to the 4th is 16, u is going to be 17. So to finish this off, I'm going to go integrate from 1 to 17, which is my new limit. 2 pi, that didn't change. I still have the 1/3, but y cubed dy, that became 1/4 du. And 1 plus y to the 4th was u, so I just have root u. Okay, so if I simplify this a little bit, 1 to 17, so this is going to be pi 6 root u du. Okay, we've done this a million times, it feels like. So this is pi 6 times 2/3 times u to the 3/2 from 1 to 17. So we get pi over 9 times 17 root 17 minus 1. And this one I did approximate / stole it from the book. Boom. Super, so that's it. So that's surface area in a nutshell.